Somewhere in space, an object is bending time itself so hard that 1 second near its edge equals years back on Earth. That's not science fiction. That's a real place. And nobody, ever, has seen what's inside it. What is actually inside a black hole? Let's set the rules first. We're not talking about the swirling movie poster void with sound effects and a hero flying through it. We're talking about the real thing, built from real math, confirmed by real telescopes. No guessing, no fantasy physics, just what the evidence actually says is waiting past the point of no return. By the end, you'll understand why some of the smartest scientists alive still can't fully agree on the answer, and why that disagreement might be the most fascinating part of the whole story. Let's start at the edge, because the edge is stranger than most people realize. Every black hole has a boundary called the event horizon. Cross it and you're not coming back. Not because of some invisible force field, because space itself is falling inward, faster than light can escape outward. Light is the fastest thing in the universe, 186,000 miles every single second. Inside that boundary, even light loses the race against falling space. Think about that. The fastest thing that exists cannot outrun this collapse. What chance would anything else have? Now picture yourself approaching one, feet first, falling toward a black hole the mass of a dying star. Here's stage 1 of the descent. Gravity doesn't pull evenly on your body. It pulls harder on your feet than on your head, simply because your feet are closer to the source. That tiny difference in pull stretches you, millimeter by millimeter, then meter by meter. Astrophysicists actually call this spaghettification. It's a real, published term, not a joke invented for the internet. Your body would be pulled into a long, thin strand, like dough stretched by invisible hands. For a small black hole, born from a collapsed star, this stretching happens violently before you even reach the horizon. You'd never survive the approach. But for a supermassive black hole, millions or even billions of times heavier than our sun, the stretching is far gentler. You could, in theory, cross the horizon in one piece, feeling almost nothing unusual in that first moment. That's stage 2, and it's where things get genuinely strange. From your own point of view, falling in, crossing the horizon, might feel completely uneventful. No flash of light, no wall, no alarm, just empty space sliding past. But from far away, someone watching you fall would never actually see you cross that line. Time itself stretches near the horizon. To an outside observer, your image would freeze, dim, and redshift into darkness, appearing to take forever to fall in, even though from your perspective, the fall simply continues. Two completely different truths, both mathematically correct, depending entirely on where you're standing. That's not a metaphor, and it's not a trick of language. That's Einstein's general relativity, doing exactly what its equations have predicted for over a century. There's one more wrinkle before we go further. Physicists distinguish between two kinds of black holes here: the small, stellar mass kind, born from a dying star's collapse, and the supermassive kind, sitting at the center of nearly every galaxy, including our own. The tidal stretching that would tear you apart near a small black hole is almost gentle near a giant one, purely because of geometry. A bigger black hole has a much larger horizon, which means the difference in gravitational pull between your head and your feet, at the moment you cross, is smaller. Size, in this one strange case, is mercy. So what's stage 3? What's actually waiting once you're fully inside, past the point where light itself is trapped? Here's where the honest answer gets complicated, because there isn't just one. The classical answer, the one that falls directly out of Einstein's equations with no extra assumptions, is a singularity, a single point where matter is crushed into infinite density and zero volume. Space and time, as we understand them, simply stop making sense there. Mathematician Roger Penrose proved in 1965 that under very general, realistic conditions, a collapsing star must form a singularity, work rigorous enough that it earned him a share of the 2020 Nobel Prize in Physics. For decades afterward, that was the accepted picture in textbooks. Fall long enough, and you hit a point where the laws of physics simply break down and stop giving answers. But here's the twist most people never hear, because it rarely makes it into the popular version of this story. Almost every physicist studying this today will tell you the singularity is probably not the true final answer. It's the point where our best theory, general relativity, quietly admits it doesn't know what happens next. Physicist Stephen Hawking spent much of his career on the flip side of this exact problem. He showed that black holes aren't perfectly black at all. They slowly leak faint radiation and evaporate over almost unimaginable timescales, a discovery now known as Hawking radiation. But that discovery created a brand new nightmare for physics. If a black hole eventually evaporates completely and vanishes, what happens to everything, and everyone, that fell in along the way? Does all that information simply disappear from the universe forever? Basic physics insists information cannot just vanish. This is the black hole information paradox, first framed by Hawking himself, and it remains one of the most fiercely debated open problems in all of theoretical physics, 5 decades later. So researchers went looking for alternatives to the singularity itself. Physicist Samir Mathur, working from string theory, proposed what's now called the fuzzball model. Instead of a single, infinitely crushed point, the interior might actually be an enormous, tangled structure made of vibrating strings, filling the entire volume where the singularity was supposed to sit, with no true sharp horizon and no true singularity at all, just an incredibly dense, fuzzy quantum object. Other physicists have explored equally exotic alternatives, with names like gravastars and non-singular collapse models, objects designed to mimic a black hole perfectly from the outside, while completely avoiding that infinite density point on the inside. Here's the science and data reveal, and this is the part grounded entirely in what we've actually measured. We haven't directly seen any of this interior structure. What we have seen is the shadow a black hole casts on its glowing surroundings. In 2019, the Event Horizon Telescope collaboration, an international network of radio dishes acting as one telescope the size of Earth, released the first ever image of a black hole's silhouette, the supermassive giant at the center of galaxy M87, roughly 6.5 billion times the mass of our Sun. In 2022, the same team followed it with an image of Sagittarius A star, the much smaller black hole sitting at the very center of our own Milky Way galaxy. Both images matched Einstein's century-old predictions almost perfectly, down to the shape and size of the shadow. That's powerful evidence that the outside of a black hole behaves exactly as the math says it should. Researchers have also tracked stars whipping around Sagittarius A star at astonishing speeds, one star completing a full orbit in roughly 16 years, work that helped earn 2 astronomers a share of the 2020 Nobel Prize in Physics for proving a supermassive black hole really does sit at our galaxy's heart. But every one of these results describes the outside. The inside, what's actually sitting past the horizon, remains completely unobserved, because no signal, no light, no information of any kind can ever climb back out to tell us. So what's the real answer? Here's the twist, stated as plainly as possible. Nobody actually knows, and that's not a cop-out. That's the current honest frontier of physics in this decade. The classical math says a singularity. Multiple serious, competing frameworks, from fuzzballs to quantum gravity corrections, suggest something stranger, something that avoids true infinity altogether. Upcoming tools, next-generation gravitational wave detectors like the Einstein telescope, could eventually catch faint echoes from a black hole merger's aftermath, tiny ripples that might finally offer indirect clues about which picture is closer to the truth. And it's worth saying plainly, this uncertainty isn't a failure of science. It's the opposite. Every one of these competing ideas, singularities, fuzzballs, gravastars, is a rigorous, mathematically consistent attempt to answer an honest question, tested against everything we can observe from the outside. The debate is exactly what real, working physics looks like while it's still in progress. Here's the modern mirror, the part that reaches past the physics. We build our entire lives around the assumption that every question eventually has a knowable answer, that enough curiosity and enough effort always earns you certainty in the end. A black hole is nature's blunt reminder that some boundaries genuinely hide their contents, not because we haven't looked hard enough yet, but because the universe itself may be built to keep certain secrets permanently sealed behind a horizon. So the next time you look up at the night sky, remember this: Scattered quietly across that darkness are places where the universe drew a line even light cannot cross. And on the other side of that line, our best theories, our sharpest minds, and our most powerful telescopes still cannot tell us, with certainty, what is actually inside.